ma'am.
How are you all doing today?
We're great, ma'am. How about you?
Fine, ma'am.
Good. Maybe we'll wait for another minute for it to be 12 for everyone to come and then we can start. Okay, so Tanish, should I go ahead and start or should I wait for a couple more minutes?
I think you can start now.
Okay, that looks like there are quite a lot of students. So, okay, so before we start, I just want to make sure, does everyone know how to use the chat feature of your
Yes,
Zoom?
ma'am.
And
Yeah. Yes, ma'am.
in the chat, I just want to make sure, does everybody know how to send a private message? Not a message to everyone, a private message to someone.
Yes, ma'am. Yes, ma'am.
Okay, if you don't know, then when you go to when you go to the chat, you will see over there to everyone. So you can just click on the drop down menu and send a message to someone. The reason I'm saying this is because I'm going to put a question on the screen and I want you to think about the question for a minute. And then once you know the answer, I want you to send the answer to me in a private chat. Okay, so don't send the answer to everybody in the group. I just want you to think a little bit about which of the two functions, A or B, represents an exponential function. And when you know the answer, just type A or B and send it to me in a private chat. And once again, I want to hear the answer from everyone, not just from a few students. So everybody send me the answer. It doesn't matter if you're not sure. You can write the answer and say, I'm not sure. And that's also okay. Okay, another 10 seconds. Whoever wants to send your answers, please send them. Anushka, you have your hand up. If you want to say the answer, you have to wait. Did you have a question about something?
No, ma'am. I wanted to explain the answer.
Yes, yes. So give me 1 minute. Let me wait for some more people to answer and then I'll ask you to explain.
All right, ma'am.
Okay, so a lot of people have messaged me the answer B. Some people have said it's not sure or they're not sure if it's correct. So let's actually see why the correct answer is B. But let's see why. So Anushka, can you tell me why B is the correct answer?
Yes, ma'am. So as we can see in the function A, the first term is 3, 7, and 11, and you keep adding 4. But in function B, you're multiplying each term by 3 starting from 2. So because multiplication is repeated addition, this one is exponential because it's going to be a lot faster. It's going to have a lot faster growth than the first function.
Right. So that is one thing. I'm going to stop sharing for a quick second because I have a technical issue with my iPad. But I want to also hear the answer from one more person. So I think Agraja, you also had your hand raised. Can you tell me what your thought process was?
Ma'am, it was same. In the first, when the addition was done, that is adding 4, and in the second one, there was the multiplication by 3. Ma'am, your mic is mute.
Thank you. So whenever we have a function where we constantly add something over and over, that's different from when we multiply the same number over and over.
Yes.
So one of the things that we saw in the session yesterday is that when we have an exponential function, the big thing that tells you that a function is exponential is when you have the same number multiplied over and over. So one example that we saw was the example with the chessboard yesterday, where you're putting double the grains each time on the chessboard. Or we saw the example with the rabbits yesterday, where the rabbits triple in number. And sure enough, we are seeing over here that what's happening is when I go from 1 to 2, the number gets multiplied by 3. 2 times 3 is 6. When I go from 2 to 3, the number gets multiplied by 3 again. 6 times 3 is 18. And 18 times 3 is 54. And as Adraja just explained, we also have, and also Anushka said this earlier, when we look at the function on the left, 3 plus 4 is 7. 7 plus 4 is 11. 11 plus 4 is 50. So what happens when you have a linear function? So a linear function is like the function a on the right. So if your function is linear, what's going to happen is let me try and draw the graph here. So you have 1, 2, 3, 4, and the value of the function was 3. For 1, the value was 3. For 2, the value was 7. For 3, the value was 11. So it is just going up by the same number each time, right? And so what happens is you can draw this graph as a straight line. So this is why this is called linear. Because you add the same number again and again, the change that is happening is constant. So in this case, what happens is the number added is constant each time. So that's the definition of a linear function. But on the other hand, if I want to think about an exponential function, what happens with an exponential function is, well, I started with, let's say, for example, if I start with 2, 2 times just 1, like, just 2 taken one time is just 2. And so that means that is 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8, right? And so on and so forth. So I want you to think about, so what we're going to do is we're going to split into breakout rooms in a minute. But what I want you to think about is what the graph of this function will look like. If you're going to multiply instead of adding, maybe one thing you can do is you can plot the points and see what the shape of the graph will look like. Is it a line or is it something else? But before you go into breakout rooms, I want to ask you one more question. Does anyone know what 2 to the minus 1, 2 to the minus 2, and 2 to the 0 is?
Reciprocal
Yes.
of the
Reciprocal
ma'am.
of
Ma'am,
integer
just
power.
1 upon 2
1
raised to
upon
1.
2 to the power 2, 1 upon
And
2,
one.
and 1 over
Ma'am,
0 is 1.
Ma'am, any non-zero in integer raised to 0 is 1.
Right.
2
So
to the
any
power minus
non-zero
1.
Ma'am, 2
integer,
to the 1 by 2.
2 to the power minus 1 is 1 by 2. 2 to the power minus 2 will be 1 by 2 square.
1 by 4.
okay, and 2
And
to
2
the
to
power
the
0
power
is
0,
1.
1.
Right. Okay, good. So one way to think about this, I know sometimes, like we just accept this as fact, right? If you say 2 to the power minus 1, it is going to be the reciprocal. Let's see why this is true. So see, if I was to draw a table, okay, now in the table, or I'll write the numbers in order. So I'll start from minus 2, minus 1, 0, 1, 2, 3, 4. This we already know what happens. 2 to the power 1 is 2, 2 to the power 2. So this is 2 to the power x. This is just x. 2 to the power 2 is 4, 8, 16. So each time when we are going down, we have to multiply the number by 2. So if you go backwards, what do I need to do? Like from 16, how do you get 8? How do you go backwards?
Divided by 2.
Divide by 2. You have to divide by 2, right?
Yes.
So 2 divided by 2 is going to be 1. 1 divided by 2 is going to be 1 half. 1 half divided by 2 is going to be 1
1 fourth.
Yeah. So the way you can think about this is if I'm going from one number to the next down, then what I have to do is I have to multiply by 2. But on the other hand, if I'm going up, then what I have to do is I have to divide by 2. So this is how you can see the connection of an exponential function. What you're going to do when you go into breakout rooms, let me do a new share. So right now I'm going to share this folder with you. So this is the folder for today. And let me just put this in the chat. So if you can access the link that is on the chat, it should take you to this folder. I'm just going to open one Jamboard for breakout room 1. You're going to open the Jamboard that is for your breakout room, just like yesterday. So for 2, I have already done the table, right? So you can fill this up very quickly and just try to draw the shape of the graph. And then on the next page, you're going to try to draw the shape of the graph for 3 to the x. And this is the interesting part. Then on the third page, you're going to try to draw the graph of 1/2 to the power x. So think about what 1/2 to the power x looks like. Does everyone understand the instructions, what we are supposed to do when we go to breakout rooms?
Yes, ma'am.
Can I see some thumbs ups from the reactions button on the bottom? You can choose a thumbs up. On the Zoom only, yes, very good.
Ma'am, please explain once again.
Right, so when you're going to go to the breakout room, can you click on the link that I just put in the chat? Are you able to access that Google Drive folder?
Yes, ma'am.
Okay, so in that folder, you will be doing the problems on the first 3 slides. So you have to make the table for 2 to the power x, just like I made the table right now on the screen. And then you have to make the table for 3 to the power x and also for the table of 1/2 to the power x. And once you do this, you're going to draw the graph. So just let me tell you what the table should look like. So for 2 to the power x, I have made the table like this. So you're going to make the same table and then also make the table for 3 to the power x and for 1/2 to the power x. Okay. Good. We'll come back in about 10 minutes to discuss this. Okay. Tanish, can you open the breakout rooms?
Yes.
And then Tanish, can you also assign the volunteers to just randomly assign them room 1 to 11?
Yes, I'm doing.
Urvi, are you able to hear me? Okay, she is gone. And Krutinaya? Krutinaya, can you hear? Okay. Does everyone have at least one volunteer in the breakout room?
No, we are short of one volunteer. There's nobody in room 11.
I'm back.
Oh, okay. Hi,
Got
Vinay.
disconnected. Hi, sorry.
No, that's okay. So, yeah, I'll go start with room 11 and I'll work my way up from room 11. And then, Vinay, are you joining us for the whole session?
Yeah, I am.
Okay. So then, Vinay, why don't you check on room 1 and, like just go to each room.
Sure.
Like, so what,
Yeah.
I don't know what I usually do is, since there's already a volunteer, I just go in and observe and, I'll direct some questions for 2 minutes and immediately like jump to the next room. So that's what.
Sure. Yeah.
And Tyler,
Yeah.
maybe you can start with room 4. Yeah.
Okay. Reshma, my internet is a little weak, so the video is off.
No, that's okay. I was just looking at the different Jamboards.
Okay, okay.
Okay, so it looks like a lot of you have done very productive graphs, and I want to share some of these because they look so nice, and I'd like to talk through some of them. So let me first start with, okay, first I want to start with breakout room 6. So can someone from breakout room 6 please explain how you all came up with the shape of the graph?
Yes. So on the x-axis, we first took the value of x as 1, and then we, for the value of y, so 2 raised to x, we came up with the value of y, which is when x is 1, 2 raised to x is 2. So we took y as 2. And similarly for all other points.
Okay, and so Arya, right? Arya, who else was in your group?
Ma'am,
I think Agraja and
even I was there.
yeah.
I'm Prerna.
I can't see who's talking. Can you tell me your name?
I'm Prerna.
Prerna. Prerna, can you tell me why the shape looks like this? Why is it not a straight line?
Because the values, they increase exponentially. They don't have like a common difference.
Right. So it's like the change is not constant, right?
It's not constant, it
ratio
varies.
is constant. Yeah. Exactly. And then Krishna, you had your hand raised.
Nothing.
Okay. Okay, so good. So this is a good way of seeing how the graph actually goes up on one side. And then who else was Agraja? You were also in the group. What is happening on the left side of the y-axis?
Ma'am, on the left side of the y-axis, there are the negative integers, and when we will take out the 2 to the power negative integers, at that time we will reach to the fractions. And as when the x is equal to infinity, the graph is touching at the x-axis at the point y, that is 0.
Right. So when we keep going on the x-axis, so it almost looks like it's touching 0, but we'll actually stop here for a second because it's not actually going to touch 0. But oh wait, or were you saying that it touches the y-axis at 0?
When it approaches infinity, it will appear to touch 0.
It will look like it's going to touch 0, but it won't actually touch 0. Okay, so this is good. This is a good representation of what the graph of 2 to the x looks like. And then I also wanted to talk to, okay, let me, I have a lot of breakout rooms open. So let me try to figure out which room I wanted to talk to. So, right, so breakout room 1, I want to go to the last graph, the graph of 1/2 to the x. Can someone from who was in breakout room 1?
Ma'am, I was there.
Okay. Simran, is that you?
Yes, ma'am.
Simran, can you explain what is what is the logic behind this? Your graph looks almost like it's the opposite. So why is it going like this?
Yes, ma'am, because 1/2 is the reciprocal of 2, and the graph looks opposite of 2.
Yeah, so looking at your table here, it looks like the values of 1, 2, and 3 are going to be 1/2, 1/4, and 1/8. The value at 0 is going to be the same, which is 1. And now the opposite thing happens, right? When you have negative values, 1/2 to the power -1 is going to be +2, because again, it will become the reciprocal. Or 1/2 to the power -2 will become +4. So this is a really interesting way to look at the graphs of these exponential functions and see what is happening. So let's tie this all together.
Ma'am,
Yeah.
in this the screen you're sharing, one when the power of the value of x is 1 in breakout room 1, can you please share the screen again?
Yes.
So when the value of x is 1, why is 1 by 2 ki power 1 equal to 7 by 2?
Oh, that is, I think, 1 by 2.
It is 1
They
by
have,
2.
it is, yeah, it is 1 by 2, right?
Yes, ma'am. I'm sorry.
No, that's okay. It's very difficult for me also to write with the
Yes, ma'am.
mouse.
You couldn't even plot it in the graph because it's
No, I can, that is why for some of them I had the post-its actually, because I was hoping that maybe the
Yeah.
post-its will make it a little bit easier to share.
We can't use it in
Over
the
here,
graph.
what we can observe is that when we have 2 to the power x graph, the value of 2 to the power x increases as x increases. But over here, the value of 1 by 2 into 1 by 2 to the power x decreases as x increases.
Exactly. So there are two opposite things happening, right? So whenever you have a number that, and so what is the difference between these two numbers, 2 and 1/2? Like what changed?
They are reciprocal of each other.
Reciprocal.
The reciprocal.
Okay, so now instead, so let me ask you this. Suppose I take 10 to the power x. Will the graph look like 2 to the power x, or will it look like 1/2 to the power x?
2 to the
It will depend on whether x is positive or negative.
It depends on, yeah. Okay, so it depends on whether x is positive or negative, whether it will go up or whether it will be flat. But so what is so special about half? Well, like that, like for half the value is decreasing.
It gets inverse because when we have half, we are basically finding the reciprocal of all the values that we found in 2 to the power x. So reciprocal, so for 4 we are having 1 by 4, and then for 2, when 2 is smaller than 4, but 1 by 2 is greater than 4, therefore it is decreasing, and therefore we are getting a graph like that.
Yeah, so one of the other things that I want to add, so is this just for half, or can we think of other numbers for which also the graph will be decreasing?
Ma'am, all 1 by x, 1 by
x is an x.
Ma'am, all positive integers.
For all fractions.
Yes.
fraction.
The
Ma'am,
For
fraction.
all fractions. Okay, so I'm going to try to modify what you said just a little bit more. So it's not just for all fractions, it's actually for any numbers that are smaller than 1. So any number which is smaller than 1, the same thing will happen. And any number that is larger than 1, it's going to increase, right? Any number that's bigger than 1. So if I take 2 or 3 or 5 or 7 and raise it to the power x, the powers will keep increasing. But if I take 1 over 10, 1 over 5, or even if I take 9 over 10, it's a number that's smaller than 1, right? So each time what happens is the number gets smaller and smaller and smaller. Does this make sense?
Yes, ma'am.
Yes.
To everyone? Okay, so the graphs are also making sense to everyone?
Yes.
Can I get some thumbs ups to see if everyone understands? Okay, good. So let me actually go ahead and I'm once again having a little bit of trouble with the screen sharing. So I'm going to try to write on a Jamboard.
Our group, that is group 7, we kind of used a software to make the graph, so that it comes out neat and like precise. Now you can see the Jamboard.
Hang on a second. Let me just open. This is room 7, you said?
Yes, ma'am.
Okay. Oh, okay. Can you explain again? How did you get this graph?
Yes, ma'am. So basically, we use the software of GeoGebra, and in that software, we inserted that f y is equal to 2 to the power x, whatever 1/2 to the power x or 3 to the power x, and that way we got this graph. So in this graph, again, we can see that it is coming down as the value is like, or the value of half is decreasing, and at the end, we can see that it becomes 0, but it's actually not 0. Since it is zoomed out version, it looks like almost 0, but it is still like very low, but it never touches 0.
Yeah, and that's really nice that you all were able to, and especially when you work with things like GeoGebra or Desmos, you can actually zoom in you know, in this part over here, you can zoom in and actually see that it's going to be, you know, it looks like it's almost flat and touching the x-axis, but when you zoom in, you'll see there's a little bit of space between the two lines, and it never actually touches the x-axis, right? So even if you say, for example, if you take 1 over 2 to the power 1000, it's going to be a gigantic number. Remember the chessboard yesterday? So the 1 over that will be a very, very tiny number, but it's still not going to be 0, right? It's just going to be a number very, very close to 0. That's good. Thank you for sharing. Thank you so much. Okay, so let me now try to talk a little bit about one of the other. So why did I show you all these two graphs? So the two graphs that we were looking at. So I won't look at 3 to the x. I'm just going to look at 2 to the power x and 1/2 to the power x. So 2 to the power x looks like this. And 1/2 to the power x looks like this. Right? So yesterday, I'm going to write this in blue. So yesterday, we saw this example with the rabbits. Does everyone remember that?
Yes, ma'am.
Yes, ma'am.
So we had 40 rabbits to start. And what we said was going to happen is that the number of rabbits is going to triple every week. Right? Does anyone remember what the equation was that we came up with to describe the situation?
Yes,
40 to
40
3
into
2
2 to the power
power
n
n minus 1.
40 into 3 power.
Okay, lots of people talking at the same time. So I'm going to call on Dhwani. Can you repeat what you just said?
Yes, 40 into 3 power t minus 1.
40 into 3 to the power t minus 1. And this we said is if the first week was, if you were saying 40 rabbits were there in the first week. But if we say 40 rabbits to start means this is, if suppose we say week 0, then we did say that it's just going to be 40 into 3 to the power t, right?
Yes.
Yes, ma'am.
Yes.
I'm going to use this equation just because it's a little bit easier to deal with, right? So when I say at the start, usually we mean week 0, not week 1. So it triples every week. So this 40 into 3 to the power t is going to give me the number of rabbits in week t. Another quick example I want to remind you of. The same example we also said what's going to happen is the second example was what if it triples in every 2 days?
2 days.
Yeah. So I want to see some raised hands now, just so that everyone is not talking at the same time. Can people raise their hands so I can see? So unfortunately, I'm trying to see everyone who has raised their hand. Meera, can you tell me which was, what was the formula for the second kind?
3t by 2 into x.
So you had 3 to the power t by 2, right? And
Yes.
can someone expand a little bit on this? So who else? So Harini, you also have your hand raised. Can you explain a little bit more what was in this particular situation?
Yes, ma'am. So here we started out, we didn't know the number of rabbits. So in our group in the last breakout session, we assumed it to be x.
Oh,
so
assume it's still 40, same 40 rabbits.
Okay, ma'am. So we started out by drawing a table. So for the number of days and then the number of rabbits. So in 2 days, it tripled. And then in 4 days, it tripled again. And so on and so forth. So we would see that we saw a pattern between the number of days and the power of 3 when we wrote. So suppose, yes, ma'am, can you please just draw that graph? So suppose in day 0, we started out with 40 rabbits. So in day 2, it tripled. So it was 40 times 3 raised to 1. In day 4, it became 40 times 3 square. And in day 6, it became 40 times 3 cube and so on. So we saw a relation between the number of days and the exponent of 3. So in day 2, it was 3 raised to 1. In day 4, it was 3 square. And so we deduced that on day n, it would be 3 raised to n by 2.
Right. So if you look at the exponent, all the yellow circles that I'm drawing, when 4 is the number of days, the exponent is 2, which is 4 divided by 2. When 6 is the number of days, the exponent is 3, which is 6 divided by 2. When 8 is the number of days, the exponent is 8 divided by 2, which is 4. So that way you can see that every time you're dividing the number by 2, right? Okay. That being said, okay, why am I reminding you of this? Because now I want to talk about the other direction. So what we are talking about in this entire blue part that I've written, it's very similar. So if I have to draw a graph for how the rabbits will increase, it will look like this blue graph, right? But suppose I want to model a situation in the opposite way, like what happens when something is going down. So this is an example that I want to talk about, where I'm basically going to talk about something that we call the half-life of a substance. So if Vinay, if you're still here, it would be nice if you can also, did batch PNC students also attend the session yesterday?
Yeah, they did. So I'll just make them recollect. So guys, if you recollect, in yesterday's session, Professor Clemency was giving the example of that tablet, right, which was thousands of years old, that clay tablet.
Yes, yes.
And a question that would have come to your mind is, how do we know it is 4,000 years old? How do we know that? How can we say that it's not 5,000 or 6,000? How did they come to that number 4,000? So I think what Reshma is going to explain will help us understand how exactly do historians and what do you call that, archaeologists, they come to that particular number along with some mathematical derivation. So yeah, Reshma.
Thank you so much, Vinay. Yeah, and it's really nice that when I found this out this morning, because it can help you connect and explain a little bit more of the mathematics of these historic relics and things that archaeologists find and how they really date these objects. So something that's very commonly found that helps us dating these objects is a substance called carbon-14. So I'm going to write that down here. And carbon-14 has a half-life of 5,700 years. It's approximately 57, 5630 something, but I've just taken a round number to make the calculations easier. So the approximate half-life of carbon is 5,700 years. Now, what does this half-life mean? Let's say I start with 100 milligrams of carbon-14. So what is going to happen is after 5,700 years, I'm going to get 50 milligrams of carbon-14. So what this means is the amount of carbon-14 has gone from 100 to 100 times 1/2. Let's say another 57,000 years go by. So that is after another 57,000 years. What does that mean? Another 57,000 years means total 57,000 times 2 years.
Yes, so 25 grams will be left.
Yep. So we will have 25 milligrams left. But 25 milligrams is the same as 100 times 1/2 times 1/2. Right? 2 times I've multiplied 1. Okay. So suppose I'm trying to think about what's going to happen after 5,700. Have I been saying 57,000? I mean 5,700. Times 3 years. What will happen is, so how do I find out? 25 and all is a little easy to calculate. Now it gets a little bit more difficult. So how I can calculate is I will have 100 times 1/2 times 1/2 times 1/2. 3 times. Now if I try to write this as an exponent, I have 100 times 1/2 to the power 3.
Or now we can write it as 100 upon 2 to the power 3.
100 upon
2 to the power 3.
Yes, ma'am.
Yes, of course. We can also write this as 100 divided by 2 to the power 3.
Or 100 into 2 to the power minus 3.
Or yeah, absolutely. You can also use a negative integer. So usually what we try to do is, There's unfortunately some carpentry work going on in my house, so you can hear, and my apologies for this. Give me Okay, so what we can do is we can express it in all these different forms, but usually we like to express it as a separate number to a power. So the way I've written it as 1/2 to the power 3. And the reason we try to do this is because typically an exponential function looks like some number to the power x, right? So we want to leave it like that instead of writing -3 or divided by 2 to the 3 and things like that. Okay, so let me try and now convert this into a model. So remember how for the rabbit example, what we did was, because it was every 2 days, right? So I saw the relationship between the number of days and the exponent. And what we said is, if the number of days is 6, then the exponent is going to be 6 divided by 2, which is 3. So can someone see what is the relationship between the number of years and between the exponent in this case?
Ma'am, the number of years, if it's x, then the exponent is half to the power x.
So, but the number of years is 5700 times 3, but the exponent is only 3. So how do I make that connection?
Oh no, ma'am, like if the year is 5700x, then it will be half to the power x.
Okay, to the power of that x. Agraja, you also unmuted yourself. Can you tell me what you were thinking?
The number of years is written in the power at the fraction when we are writing.
So basically, ma'am is telling that it is
here 3 years are here
Go
3
ahead. Yeah.
here 3 years are there. So in while writing the fraction, we are putting the exponent as the 3.
Okay. So I understand the confusion. It's not
Right,
actually
the half.
It's not 3 years. It is 5700 into 3 years.
Yeah. So
Yes, the whatever is the value when we are multiplying it by how much years we need to find.
Exactly. Okay. Urvi, you also have your hand raised.
So I think it will be of the form 100 into 1 by 2 raised to number of years by 5700.
Okay. So let's try that. 100 into 1/2 to the power t divided by 5700. So I'm going to give everyone a minute to just think about this for a second.
T is the total number of years, right?
T is the total number of years. Yes. So if it is 5700 times 3, then it is 5700 times 3 divided by 5700. So you will get exactly 3, right? Okay, this is great. So this model will tell you the amount of carbon at a time t. This is actually the model for finding carbon 14, right? So let's say there is a particular substance, that's found, like a particular kind of object that you find, and in its very new form, like before it starts decaying, how much carbon 14 it is supposed to have, right? And so that's the initial amount, that is the 100 milligrams or whatever. And now it has decayed over time. The archaeologists have found this, and now they want to find out, okay, how many years has it been? So this is the model that they are going to use to find that out. Now for small numbers, so say for example, suppose I was to ask you if it has become 25 grams, then you know that 100 has become half twice, right? So that you can easily calculate mentally. But if I ask you like a different number, like say for example, currently the amount of carbon 14 that you have found is only 5 mg. So what will happen is, so let me try and write this on a separate page. So let's say if I start with, so I'm going to write down the model here again. I have C of t equals 100 times 1/2 to the t divided by 5700, right? Suppose we find something with 5 milligrams of carbon 14. So what I'm going to do, so 5 milligrams means that is the current amount, right? So what I can do, what this means is that C of t is equal to 5. So then I can just try to solve this equation. And if I try to solve this equation, so what's going to happen? So let me try and do the usual. I'm going to divide both sides by 100. So I get 1 divided by 20 is 1/2 t to the power t over 5700. Now this equation is a little bit difficult to solve because in the equation the exponent has the variable. So in order to solve an equation like this is when we use logarithms. So let me give you an example. So say for example, this is a different example over here, okay? Let's say if I tell you x squared is equal to 4. How will you find the value of x?
We'll find the root of 4, so square root of 4.
Find the square root of 4. Right. So if you find the square root of 4, that's going to be x, right? That's how you do this calculation. So similarly, now square is a kind of function. The only way to undo a square function is to take the square root. So similarly, the exponential function, when you want to undo it or when you want to reverse it, we use the log function. Now we don't have time in today's class to talk about log functions as well, but it's just an example I wanted to give you. So for example, if you want to solve this equation to find out how many years has it been before the amount has become 5 milligrams, then you would just solve the equations using logarithms and that would actually give you the value. So this is a really easy way in which you can date a lot of objects if you know what the half-life of certain substances, and carbon is something that everything is made up of, right? So knowing the half-life of carbon really helps to do this. Kirti?
Yes, ma'am, but how would we know that the carbon started as these many grams so many years ago?
So that I think depends. So this is something I don't fully know. Maybe Tyler can answer this, but I'm assuming that's because we know in certain substances, like what is the carbon that exists in its before it decays.
Okay. I mean the total carbon percentage or carbon content of that substance when it is manufactured or made.
Yeah. Tyler, do you have a better answer for this? Are you here in this meeting?
Yes, I'm sir is there.
You're on mute if you're trying to talk.
Yeah, sorry, I'll put something in chat.
He's actually downstairs in the same house, so there's a lot of noise with the carpenter where he's sitting. Meera, you also had your hand raised at the same time.
I was also having the same doubt.
Yeah. Shreya?
Yes, ma'am. I had an idea about that because when a plant or a living thing is alive, the carbon in it is mostly carbon 12 or carbon 13. But when it's dead and when it starts to decay or when there is no more regeneration in it, the carbon is converted to 14. So the carbon 14 is only for the time until the plant is dead. So carbon 14 will only equate only after the death of that living thing.
Right. So the Tyler has sent in an answer saying in the environment, the ratio of carbon 14 and regular carbon 12 stays the same. So he's actually a chemist, half a mathematician. I'm only a mathematician. Once the plant dies, it stops adding carbon 14 and then the carbon 14 turns into something else as it decays. So pretty much similarly, very similar to what Shreya, what you were saying. Simran, you also have your hand raised?
Yes. Ma'am, how can we know that it has become half after 5,000, 50,000, 100 years?
So that is by actually, so we can actually study how something, so this is a really good question. So if you just study how something is decaying over time, so let's say if you see how much a substance has decayed over 5 years, maybe it has not reduced by, of course, if it takes 5,700 years to reduce by half, nobody is going to be alive, right, to see how much it has decayed. But maybe over a period of 10 years, you can see that it has reduced by 1% or reduced by 2%. And that can help you extrapolate and figure out what the half-life of a substance is, right? So like, for example, if you're thinking that, oh, like in this much time, it has reduced from 100 to 99. and in this much time it has gone from 100 to 98. Then you can just do the calculation and figure out when it will get from 100 to 50, right? That's a really good question. Thank you. So Tyler says we actually have really good data now from the last 100 years. So carbon 14, usually, as I said, you observe it over a few years, and now because the scientific method, people have been doing all these experiments for enough decades now that we have enough examples for the last 100 years. Swasti?
Sorry, ma'am, I accidentally raised my hand.
Okay, no problem. And Shreya, did you still have something to say, or is your hand just raised from before?
No, ma'am. Sorry. Yeah.
Okay. So I see that it's so, Vinay, I just wanted to check in how much time do we have? Do we have time to do an example, or should I try to wrap up using the example?
I think they may have something scheduled after this, so we can take about say 10-15 minutes beyond the session. Is that okay?
Yeah, that's fine with me.
Okay.
Yeah. So I think, I just want you all to be able to see, one more like small kind of application of this half-life before, we end for the day today. Since we saw carbon dating, which is again, of course, a very, very useful thing to know. I want us to see another example that's a little bit closer to home. So, at some point or the other, most of us, if not all of us, might have taken some amount of crocin or paracetamol when we are sick, or when we have a fever or a headache or something. So this example has to do with what happens when your body takes the paracetamol. How does it, at what rate does it actually dissipate? So let me share my screen, and actually what I want everyone to do is take a minute to read the sentence that is on the screen. So does everyone understand the sentence that paracetamol has a half-life of 3 hours?
Yes, ma'am.
So there was a question in the chat about the previous carbon dating example. So somebody asked whether that equation is only applicable if you start with 100 mg of carbon. Yes, that is true. So depending on how much, so the initial value you have to know, but half-life means how much ever you start with, half of that will be there after that much time. So that is what half-life means. So in this case, paracetamol, whatever you take, half of that will be left in your body after 3 hours. Is this understood to everyone? Okay. So we are going to go into breakout rooms for just 5 minutes, and I want you all to just talk about the first page of this question, and we'll come back and wrap up. Tanish, can we open the breakout rooms just for a quick 5 minutes?
Yes.
Okay, so it's just volunteers here. We can go to some of the rooms, and since I started from 11 last time, I want to start from the middle this time. I'm going to go to breakout room 4.
Okay, sounds good. Sorry, it's quieter now. Where do you want me to start?
You can start with 1 if you'd like, and maybe Vinay can start with 11. Yeah.
Very good.
Sorry, I got disconnected. Reshma, can you tell me what is the question that you have given so that I can just Tyler, can you help?
Yeah, it's the crocin question. So it starts on frame 5.
Right. Okay. Can you share that link, over here in the chat? Yeah.
There you go. That should work.
Thanks, Menon.
And then Reshma was, I don't know if you were here, Reshma was suggesting that you can start with room 11 or with the high numbers, and I'll start with the low ones.
Okay, okay. Thanks for saying that. I wasn't here at that time. Okay.
Sure.
Ring 5, right? Got over a little too early, I felt.
Anish, can you send me to room 11?
Omkar,
So we're coming back in a few
over.
seconds.
Oh, okay.
I was just trying to be respectful of the time.
Yes, I'm just trying to do it, but then it closed.
We completed the graph, but then we couldn't do the next model thing.
That's okay. Who just said they completed the graph?
Ma'am,
We have also.
we completed the graph. And we were also in midst of finding a formula for the
We just found and we have not.
Okay, so lots of people talking. Anushka Tonapi, can you tell me which group, which room you were in?
Ma'am, I was in breakout room 8.
Breakout room 8. Okay.
Yes, ma'am.
Okay, so can you tell me a little bit about, that's a nice graph. It represents, I think, the shape very well. So what made you all draw a graph that looks like this?
Actually, we used Desmos to actually do it, but we really couldn't see the difference. So instead of instead of drawing the graph over there, we tried to make a rough sketch of what it would look like, because it's very close to the y-axis. Actually, it looks flat in the first few values actually.
Right. So it starts. So one thing you could think about. So I'm actually going to look at your calculation on the right here. You did 600, then 600 times 1/2, then 600 times 1/2 times 1/2, then 600 times 1/2 times 1/2 times 1/2, right? So there's a pattern here. So the way I think, like, is easy to think about this. So I'm going to use your graph only and try to see how that would make sense to draw. So let's say in the beginning, I'm looking at your table on the right, you start with 600 milligrams. So if you start with 600 milligrams, then you are, say, at some point here at 600, over here. And then after 3 hours, what happens is it comes down to half. So you're here. So after 3 hours, you're going to be over here. So I'm going to draw a little bit differently from your graph. And then after 6 hours, you're going to be half of this amount. So that's going to be over here. Right? And then after 3 more hours, you're going to be half of this amount. So that's going to be over here.
So the beginning it reduces gradually and drastically, and then after that very slowly.
Exactly. So initially it reduces very drastically, but then there is not enough in your system, right? There's only 300 milligrams in your system. So it's only going to reduce
So
by
the original value is very less. So even when you divide, it'll come even less, like multiplied. Sorry.
Exactly. So it seems like it's reducing at a very different kind of level each time. Yes, thank you guys so much for sharing. I think that is a good way to describe the graph. Let's talk about the equation now. So I think I saw breakout room 5. Can you all tell me about how you came to the conclusion that this is the equation that you have? Simran?
Ma'am, I'm from breakout room 1.
Oh, that's okay. Simran, did you all also arrive at the same equation?
Miss, I got the equation. F bracket T is equal to 600 into 1/2 upon 1/2 to the power of T by 3.
Right. So why is that the equation? Why does that make sense?
After observing the pattern, I got that 3 hours, I should multiply 600 into half, and that is uh, 1 by 2, that is 3 hour by divided by 3, it should be 1. And after 6 hours, I got 600 into 1 by 2 into 1 by 2, that is 600 into 1 by 2 to the power of 2, and 6 is divided by 3 to get 2. So after observing this pattern, I got the equation.
Okay, thank you so much, Simran. Urvi, you also have your hand raised. Did you want to say something or ask a question?
No, ma'am. I'm from breakout room 5, so I was saying like even we followed a similar pattern. We found out for the first 4, then we just generalized the statement and brought it in the form of for n hours. It will be like 600 into 1 by 2 raised to the power n by 3.
Okay, yes, sounds good. Thank you so much, both of you, for explaining that, Simran and Urvi. So last thing I'm going to say before we go away. So yes, so this is another, as you can see, an exponential model, 600 into 1/2 to the power 3 by 3. And this tells you the amount of paracetamol in your system. So it's really nice. This is a nice way to model something, much more closer to home, something we have all experienced. So, you might have seen in sometimes on TV or in movies when somebody is doing a drug test and they take a blood test and they figure out, how much of a certain drug is in your system. How do you know when somebody has taken the drug or hasn't? It's by using exponential functions like this. So, I mean, of course, nowadays it's done using a computer, but the computer uses
They
these
predict like by
exponential
this
functions.
time this will reduce and that will increase in their body bloodstream.
Yes, exactly. So one thought I want to leave you with is this idea, and this is something for you to just think about. I won't finish this problem, but oftentimes when we take, when we are sick and we have a fever or something, the doctor just doesn't tell you to just take crocin once, right? They tell you to take crocin 3 times a day or 4 times a day. So think about what happens when you continuously take crocin 3 or 4 times a day. So if I start with taking 600, or in this case, I'm taking 1000 milligrams of paracetamol. So that's 2 doses of paracetamol in a day. And so if I start with that, what happens is I'm starting with 1000. And then after 6 hours, it will become 5. So every 6 hours, I'm going to take 2 more tablets. So after 3 hours, it becomes 500. And then after another 3 hours, it becomes 250. Right? What will happen now if so this is the 6 hour mark. What will happen now at 6 hours if I take 2 more crocin? What happens to the paracetamol in my body?
Now, that 300 grams will be there from the previous crocin, and then we'll get more 600 milligrams of it. Yeah.
Right. So this is right now I'm taking the regular strength 2 tablets. So 1000 milligrams I'm adding and 250 is there from before. So now I'm going to have
1250 grams.
Exactly. So I'm going to have 1250 grams. Then, again, the next 6 hours, it will be half of that. So that's 625. Half of that is 312 or something. So this is actually really interesting because now it becomes 312 after 6 hours. Then if you take another crocin, another 2 crocins, it becomes 1312, right? So you see how it reduces.
Yes, ma'am. Basically, whatever dose we have taken first, we first make half of that and we add 600. Then whatever value we get after 6 hours, we again make a half of it and then again add 600. And then it goes on like that.
Yeah, exactly. Thank you, Anushka. So one important thing to think about here, the question is, if you keep doing this for 24 hours, so one thing you can think about is, how these levels of paracetamol keep changing. What if you take crocin forever, for the rest of your life? Every 6 hours. Is the amount of paracetamol in your body going to explode or will it stabilize after some time? So one hint to think about this problem is you see that how initially from 1000, the paracetamol went up to 1250. But after 1000 to 1250, the next level, it only went from 1250 to 1312. So it looks like it's increasing, but it's increasing less the second time. And the next time it will increase even less. So you might want to, like, this is a question to think about. I mean, of course, nobody is going to do this because it's still bad for you. If you keep taking paracetamol for the rest of your life, it will really be bad for your liver. But
yes,
it's an interesting question to think about.
Yes, ma'am. So when we don't have an illness and we take paracetamol, the body requirement increases, and then again when we get there, we need to take double or some more amount of the paracetamol, and therefore this is not right.
Yeah. So it's just, thank you, Anushka, again for sharing that. So it's just really interesting to think about these, macro level questions like carbon dating, but also like very close to home questions like taking crocin and how exponential functions help us understand or study these. So not only things like this, but one of the other really, really important applications of exponential functions is population. So how the population of a town increases or decreases, studied using exponential functions. How so the spread of coronavirus, or like, with Omicron, now, how they are predicting that by the next week, these many cases are going to be there in the UK. How do they do that? They do that using exponential models. So exponential models and exponential functions are all around us to model a lot of situations that happen in everyday life. So I hope that when you do, see exponential functions in your school, or if you've already seen it, try to explore more of these application-based questions and see how the mathematics that you do in school is actually applied in the everyday life and everything that you see around you.
Ma'am, viruses grow exponentially, viruses and bacteria.
Yes,
Some of
bacteria
them get
grows
petri
exponentially.
dish.
So a lot of times when you're
Yes,
studying
ma'am.
bacteria in the lab, it grows exponentially. Population of
Yes, ma'am.
bacteria
There is
and
one
viruses.
problem, one famous problem, that there was one bacteria in a jar, and after every second it becomes twice. So what will be at, like,
Yes,
what will
ma'am.
be 50 grams, something like
So
that?
how many times do you need to fill it so that
Yeah.
it becomes half of the original amount? So
Yes,
if it
ma'am.
takes some 60
If
seconds
it
to become
fills
full,
completely,
how many seconds till it becomes half?
So if it's 50% after these many seconds, then how many seconds it takes to fill it? And it's exactly
yeah. So yeah, it's exactly 1 second less, because in the next second it will become twice.
Exactly. So that's the power of an exponential function. If it takes you so many seconds to fill half the jar, within the exponent means within 1 second now it has filled the whole jar. Exactly. Good. So I hope you have all learned a little bit from these two sessions yesterday and today. I've certainly enjoyed my time with all of you. I'm going to wait back if any of you have any questions or comments, but otherwise that's all from me, and I hope you'll enjoy the rest of your sessions today.
Thank you so much, ma'am.
Yes, ma'am. Thank you, ma'am.
Before you guys leave, it would be great if one of you can share your feedback about Reshma's session. Simran, would you like to say something?
Yes, sir. So it was really amazing that I learned from Ma'am Reshma ma'am, and they teach us very we get very interest, and I get inspiration from them. That is how their teaching style is somewhat different from all other teachers. It's very
Thank you so
interesting
much,
and
Simran.
amazing.
That's really nice of you to share.
I completely agree with what you're saying, Simran. Yes. A few more hands. Okay, so we'll make it quick. Okay, Anushka, Harini, and Shravani interns. 30 seconds
Yes,
each.
yeah. So I really like the sessions, and the way ma'am taught was very energetic, and the class was very lively, and we had a lot of fun in the class, and we also learned many things, like how we can apply these exponential models in our daily life, and how we learn it in math, and how it is connected to us personally. So basically I enjoyed a lot, and it was a great session. Thank you, ma'am.
Thank you.
Harini.
Yes, sir. So like Anushka said, I also really enjoyed the session. So one thing I really liked about ma'am's class was it was very interactive, and a lot of the classes which I attend, they're not so interactive. So this was a very nice change for me. I also really like the topic that she was discussing, because I really like exponential functions in general. And I also got a lot better at making graphs here.
That's really good. Thank you, Harini.
Shravani?
Yes, sir. I like her way of approaching the students. Means she is very open to explain, and always energetic. And her style of teaching is also so nice. Means I like it.
Thank you, Shravani. I'm glad you enjoyed.
Yes, Agraja.
Ma'am, thank you for this great course. I think we all have enjoyed it. I have, but I know and you means you have taught the things in such a way that it was totally got cleared. You have taken many examples, and if somewhere we were having any doubt, you were clearing it too. And ma'am, you for teaching us, you have done the traditional makeup. That was very nice.
Thank you. That's so sweet.
Thank you, ma'am.
Thank you so much once again, all of you.
So after all these sweet words, I don't feel like messing it up with my thank you notes. So what you did in the class is explicitly visible from their feedback. So thank you so much, Reshma, once again.
Thanks, Vinay. This was again such a great opportunity. Thank you all for your wonderful comments. I hope you all really enjoy and do more math applications and learn a lot more math. It's so much fun in the future. So I don't know.
Okay.
I know, Vinay, you said you wanted to take some screenshots. I don't know if that's been done. Should I wait?
Yeah,
or would you like
being.
to? Yeah.
Yeah, so we'll wait for another 30 seconds while the volunteers take the screenshots. And others who wanted to say but didn't get a chance, you can type in your feedback in the chat quickly to everyone so that Reshma can also read it. Yeah. And special thanks to Tyler. Is he there or he got disconnected? I'm not sure.
Yeah, no, he's there. He's been disconnected
I'm
many
here.
times.
Okay, yeah. Thank
Thank you.
you, Tyler. Thank you.
Okay, Jayaditya is giving a thumbs up. I'm assuming that.
Okay. I thought he was posing for the photo. So, yes. Okay, yeah. So we are done. Okay.
There's a lot
Okay,
of
Reshma.
private comments. It's going to be hard for me to respond to everyone, but thank you so much for your comments. I really appreciate it.
Thank you. And I'm sure you'll see some of them in Harvard in a few years, Reshma.
Yes. Good luck to all of you.
Yes. Okay.